Well, let's do another example. Acetic acid. Okay, tell me the chemical properties of acetic acid. So first start with metathesis. What are the metathesis properties? So what are the ions here? We got H plus and acetate. Well, H plus is an acid, so we'll deal with that in acid base, right? But let's talk about acetate. Tell me about acetate. So what do you know about acetates? Nitrates, acetates, and chlorates are all so basically no reaction. Metathesis, nothing really, no reaction, right? Well, I shouldn't say except for the acetate. There's no reaction. The H plus there's reaction. Yeah, H plus. And so H plus we'll treat that that's an acid. The acetate. This is for metathesis. NR. No reaction from it. All acetates are soluble. And so let's go to acid base. Talk about it. Now, acid base, acetic acid is weak acid. So we know this is a weak acid. And so when we do H plus, yeah, it's got H plus, but it doesn't completely break off easily. And so H plus is somewhat constrained. And so when I take a look at acetic acid, well, acetic acid, which is here, will it react with all bases? Will acetic acid react with all bases on this list? No, it doesn't react with all bases. So tell me what bases it reacts with. So for example, will acetic acid react with ammonia? If acetic acid reacts with ammonia, then acetic acid donates a hydrogen to ammonia, this hydrogen to ammonia, to form ammonium. So acetic acid reacts with ammonia to form ammonium. Is that favorable or not favorable? Well, acetic acid versus ammonium, which one's stronger? Acetic acid is stronger, so we're going from stronger acid to weaker acid. Is that favorable or not favorable? It's favorable. Will acetic acid react with fluoride? So if acetic acid reacts with fluoride, then it donates a hydrogen to fluoride to form hydrofluoric acid. Is hydrofluoric acid weaker or stronger? Hydrofluoric acid is stronger, so we're going from weaker acid to stronger acid. Is that driving force? No. So when I asked you, will it react with all bases? No, it won't. It won't react with, this is called formate, fluoride. It won't react with fluoride. It won't react with this one you should know the name of. Nitrite. It won't react with dihydrogen phosphate. It won't react with sulfate. In fact, it won't react with any base that's weaker than this one. This is acetate. It'll react with any base stronger than acetate. And so acetic acid reacts with any bases stronger than acetate. And you can just list them. There are a whole bunch here. What are the bases stronger than acetate? Bicarbonate, hydrogen sulfide ion, monohydrogen phosphate, ammonia, cyanide, carbonate, phosphate, hydroxide, sulfide, amide, oxide, hydride, methide. Those are the bases that are stronger than acetate. Okay, then that leaves what? Redox. For redox, we're not going to treat acetic acid because acetic acid doesn't occur on the redox chart. And so for redox, we just look at the H plus. H plus is what? An oxidizer. So acetic acid will oxidize what? All these or all those? H plus will oxidize these, or H plus will oxidize those up there? Which one? lower, yeah. And so acetic acid will oxidize lead, tin, iron, zinc, aluminum, magnesium, sodium, calcium, potassium, lithium. However, acetic acid will not oxidize tin 2. Acetic acid will not oxidize copper. Won't. And so it'll oxidize, any reducing agent stronger than hydrogen. What about acetate? Now, acetate doesn't occur on the chart, but we can look at acetate and based on its oxidation state. So, for example, hydrogen's happy at +1, oxygen's happy at -2. But what about carbon? What's carbon here? So +1 times 3 is +3, -2 times 2 is -4, +3 minus 4 is -1. -1 plus what is going to give me -1? That's got to be 0. So carbon's 0. If carbon's 0, that means it could lose or it could gain. And so acetate's both an oxidizer and a reducer. Is it a very good one? Is it a very good oxidizer? Not really. H plus is much better. And so this is an oxidizing agent and a reducing agent. Can you burn vinegar? Can you burn acetic acid? What do you think? Will acetic acid burn? And the answer is, if you eat acetic acid and burn it in your body, we do the same thing. When we eat stuff, what do we inhale? So we have food, and we inhale what? Oxygen. And the food is like sugars and fats, proteins. We exhale what? And generate water, and we get energy. So if we eat vinegar, do we get any calories? Can we burn vinegar? Oxidize it all the way to CO2? In other words, can we take acetic acid and oxidize it all the way to CO2? The answer is yes. Acetic acid will burn. So acetic acid is a reducer. It's an oxidizer. It's hard to place on the chart, but those are the chemical properties that we'd see for that. Okay, how about copper? Let's just do, what are the chemical properties of copper? Solid. So first we start off with metathesis. Are there any metathesis reactions for copper? No. Why are there no metathesis reactions for copper? It's not an ion. Metathesis deals with ions, so no reaction for metathesis. Is there any acid-base reactions? No. The only reaction for copper is redox, and that is copper is a reducing agent. That's it. Do one more, and that's it. CO2. What are the chemical properties of CO2? First off, we do metathesis. Are there any metathesis reactions for CO2 itself? This is very tricky because is CO2 an ion? What is metathesis? Metathesis is favorable ion combinations. So we'd say no metathesis reactions, right? It's very tricky because is there acid base for CO2? And you'd go, yes. Do you see it here? CO2 plus water. CO2 plus water gives us carbonic acid. Do you remember carbonic acid decomposes into CO2 and water? Well, whenever we have CO2 and water, we have carbonic acid decomposes into CO2 and water, but CO2 and water can mix together and form a tiny bit of carbonic acid. And so CO2 is an acid. CO2 is an acid. CO2 in water is an acid, and it will react with all bases stronger than bicarbonate or weaker than bicarbonate? Stronger than bicarbonate. So CO2 in water will react with all these. Now, I said CO2 in water has no metathesis, but if CO2 combines with a little bit of water, it forms carbonic acid. Carbonic acid has metathesis. So when there's CO2 present, this is what happened. What happened to the lime water? When there's CO2 present, we form a little bit of carbonate. Now, carbonate does have metathesis. What ions does carbonate like? Carbonate likes all cations other than group 1 and ammonia. And so carbonate can react with that. And so potentially some metathesis there. How about redox? What would you classify CO2 as? And so when we look at this, oxygen's a -2, that means carbon is a +4. At carbon at a +4, can it lose any more electrons? No. The only thing it can do is gain. So CO2 is an oxidizing agent. Is it a very strong oxidizing agent? No, it's not. However, if you have a powerful reducing agent, then you don't need oxygen to burn powerful reducing agents. We could use some very weak oxidizer like CO2 to burn it. And so this is an oxygen-free environment here. What they're doing is they're going to generate some CO2 here. So this is bubbling out CO2. You see the flame was extinguished because they used CO2 in fire extinguishers. But wood is not as powerful of a reducing agent as magnesium metal. And so all these bubbles of CO2, now they're going to take a strip of magnesium and watch what happens when they put a powerful reducer in there. You see the CO2 will, and so this is burning in the absence of oxygen. They're using CO2 as the oxidizer here. This is why you never use CO2 on a metal fire. You could use CO2 on a wood fire and put out that wood splint in a second. The wood splint here. You see it put out the match right away. But wood is not as powerful as a reducing agent as magnesium metal. The magnesium metal is, again, it's just combusting. There are lots of videos of this. So CO2 is an oxidizer, and that's why you don't use it on metal fires, but you could use it on wood fires because it's too weak of an oxidizer to oxidize wood. All right, so we talked about the metathesis, acid-base, and redox properties of that. Okay, now in an effort not to get too far behind, which I am, I'm going to start the next chapter here, which will be chapter 10. Chapter 10 deals with, this is a combination. Chapters 8 and 9 is a combination. Parts of chapter 19 were thrown in here. Not only parts of chapter 19, but also parts of chapter 17. Let me show you. I didn't want to break up the chemical reactions into a whole bunch of different. I didn't talk about everything here. Some of the stuff I left off. I just mainly talked about Bronsted acid-base reactions. So here in chapter 17, we have the acid-base chart here, similar to the one I passed out. So we have the acids here. Acids lose a proton. They form the conjugate base. Conjugate bases are here. here. This chart is actually more comprehensive than our chart. So we just talked about how to use this chart here. See, these bases here are extremely weak. Negligible ability to remove protons, or they're pretty much neutral. That's in chapter 17. So chapter 8, 9, 17, and 19 were all kind of combined into chemical reactions. This type of stuff is what we're doing on the chart. When we're looking at the chart, will HSO4 minus react with hydroxide? HSO4 minus reacts with hydroxide to produce HOH. Is that favorable? Yes, it's favorable because we're going from stronger acid to weaker acid. So this kind of diagonal stuff we're doing on the chart just now, but this is talked about in chapter 17. We're going back to chapter 10 now. Chapter 10 deals with quantity relationships. Like, for example, yes, I want to put sulfite in wine because sulfite is going to act as an antioxidant, but how much sulfite do I need to put in wine? You know, too much sulfite is going to alter the taste. Too little is going to result in vinegar, your wine turning vinegar. We just need to add just the right amount. Now, to figure out what just the right amount is that we need stoichiometry. Stoichiometry, the definition of stoichiometry is quantity relationships. So this is stoichiometry in chemical reactions, or quantity relationships in chemical reactions. This is what we call stoichiometry. And so we could do calculations based on balanced chemical equations. So the first part of stoichiometry is we need a balanced chemical equation here. And from this, we know the right amounts. For example, in this chemical reaction, for every 4 ammonias, I need 5 O2s. That's just the right amount. If I have 4 O2s, it's not enough. If 4 ammonias with 4 O2s, it's not going to work. And so these are what we call the stoichiometric ratios. 4 ammonia molecules to 5 O2 molecules. 4 moles of ammonia molecules to 5 moles of O2 molecules. So here we have, if we have 5 moles of O2, we need 4 moles of ammonia. We can also relate this to all the other species in the equation. This is a redox equation here. This redox equation, we would be doing it using skeleton or some other method here. They just gave it to us. This one wouldn't be on the chart because we don't have these. This one would be on the chart. O2 to water, yes. Ammonia to NO, no, we don't have that on the chart. But we can get these ratios. These are called stoichiometric ratios from the balanced chemical equation. And so it's a 4 to 5 to 4 to 6 ratio. So we can relate any two things here. That's what they're doing. This.